Hi, everyone. Thanks all for coming to my presentation. My name is Anindya Saha, and I'm hugely honored to be presenting today on my work on distilling representational similarity using centered kernel alignment, or CKA for short, a work that I've been undertaking as part of my PhD at the University of Queensland and Data61 CSIRO. Edge computing has really taken off in the last few years as a processing solution for data at the source of the data using edge class devices. This has really been driven by real-world computer vision application constraints such as low latency, low power, low cost, and so on. But these platforms, they tend to be quite resource constraints, which means they're limited in the complexity and therefore the accuracy of the models that can be deployed. Turns out, though, that most deep learning models, they are actually quite over-parameterized, containing a lot of redundant parameters, which means by removing those redundant parameters, we can actually optimize the models and without actually affecting any of their accuracies. Some of the major techniques include pruning, quantization, low-rank factorization, and knowledge distillation. Knowledge distillation has been sort of my primary area of interest during my PhD, because it is an end-to-end compression technique where a compact student network learns to mimic a larger, more performant teacher network. So as opposed to starting with a big network and compressing it down, it actually starts with a small network and tries to improve its accuracy by introducing context-rich information that the student can learn from. Moreover, the KD, as it's otherwise known, is also a framework and hardware agnostic model compression technique as opposed to its other counterparts. So that's an added benefit there as well. Now, there are three main ways of applying knowledge distillation. So one is the response-based distillation, which happens at the output layer of the network. This was the original basis for Geoffrey Hinton's original proposal for KD, where he expounded that the output of a teacher network actually contains a lot more information about the interclass similarities than a one-hot encoded label for image classification tasks. And so that's an example of how you can formulate knowledge with context-specific, context-rich information for the student to really benefit from. The next one is feature-based distillation, which happens in the inner layers or the intermediate layers of the network. So really the low-level representations that the teacher learns is distilled to the student. However, one main drawback for this method is that the layers that the distillation happens between, they have to be of the same dimensions. Otherwise, you can't actually apply feature-based distillation. So that's a major drawback there. Now, relation-based distillation is actually one that tries to distill any structural knowledge about the interlayer, interclass, or interexample similarities between the data set or the model itself. So that's an interesting one that I've been looking at recently. And representation distillation is an example of relation-based distillation that leverages the structural knowledge of the interclass similarities. And this was sort of, excuse me, this is sort of initially identified by Tung, where he found that semantically similar inputs elicited very similar activations. So for example, in the left-hand figure, you can see the CIFAR-10 dataset, the first 1,000 examples in the CIFAR-10 dataset actually elicited, which is of the same class, by the way, elicited a very similar activation all the way along the network. And the same goes for class 2 and class 3 and class 4 and so on. So really there's an inherent structural difference in that if you were to plot all of the instances by class, I suppose, in the high dimensional feature space, you'd see the specific classes being sort of in different clusters. So really being able to tap into that structural information as opposed to instance level congruence, which is what feature-based distillation tries to do, is actually more beneficial than that. So similarity preserving KD, or SPKD, was Tung's original proposal to apply representation distillation using an interexample similarity matrix by computing the Gram matrix. So the way that they did that was basically taking the intermediate feature map, flattening the channel width and height dimensions. So you have a B batch by CWH matrix, then basically that matrix gets multiplied with its transpose to form a B by B interexample similarity matrix, which is essentially the Gram matrix that we know. So the main benefit here, as you can see, the student and the teacher both produce a B by B matrix, which means there's no real concern for having to have the same feature map dimensions, because the Gram matrix will be always of the same dimensions, and so it's much easier to distill without any expensive workarounds. So the one problem though with SP has been that it uses the distance-based Frobenius norm to actually perform the distillation of the interexample similarity matrices, which actually turns out is not invariant to isotropic scaling. And the reason this is important is because isotropic scaling doesn't actually affect class separation. So punishing a student for having features of a different scale is not actually beneficial for it's in fact detrimental to the student. Rather, the shape of the feature distribution is actually what determines class separation, and that's what we should be really focusing on. So the centered kernel alignment CKA is sort of what it sort of comes in and with that property that we were after. And it's actually one of the most robust neural network similarity metrics that is invariant to isotropic scaling. And so how it achieves that is it centers and normalizes the Gram matrices and then computes their cosine similarities. So if you look at the CKA function here, you can see the HSIC kernel, which is the Hilbert-Schmidt independence criterion, is the one that actually does the centering and the normalization operations. All of the details are sort of laid out below. I won't get too much more into detail of that, but basically the rest of it you can see is very similar to the structure of the cosine similarity function, which we all know. So we sort of started thinking about how we could use CKA in the context of representation distillation. And given that the goal of distillation is to maximize similarity between two layers, we figured that we could actually use CKA as a loss metric to maximize the similarity between a student and a teacher pair, right? And the way we do that is basically formulate a loss function that goes 1 minus CKA of GSGT, and that basically pegs the value of CKA to 1 to maximize that value to 1. And the result is a technique that applies centering and normalization before distilling the interexample similarity matrices, as opposed to the state-of-the-art, which basically applies distillation on the non-centered Gram matrices. So the training curves kind of show here for resident 18 student and a resident 50 teacher, the CKA basically matching the teacher baseline. So you can see there's a quite significant jump up in performance compared to SP, CC, which is the correlation congruence, and RKD, which is the relational knowledge distillation. Now, looking at the training results here for Cypher 100, we can see across two student architectures, Resonant 18 and Mobile NP2, we're consistently outperforming with CKA compared to the other baseline metrics. And we also evaluated on Tiny ImageNet and ImageNet 1K as well in our paper, so you can find our paper for more information on those. But that sort of just shows the generalizability of across different architectures, different data sets, as well as obviously natural image data sets like ImageNet 1K, which is quite promising in terms of our results there. Now, we sort of were wondering what the actual components are of CKA that sort of sets it apart from the other methods, and we sort of want to conduct a little bit of an ablation study on that. So what we did was basically we computed we removed the centering kernel or the centering matrix in the HSIC kernel, and we formulated a loss function that's basically the CKA without that centering part. And turns out that basically just boils down to the cosine similarity, right? So if you just compute cosine similarity between the two Gram matrices, that's basically CKA without without centering. And so from our ablation study, we can see that CKA without centering consistently underperforms CKA with centering. And if we were to compare the CKA without centering experiment, which is the cosine similarity metric essentially, with the SP metric, which is basically the Frobenius norm, the Euclidean distance space Frobenius norm loss metric, we can see that the cosine similarity outperforms that as well. And the reason for that is that cosine similarity is a bounded loss value, which is between 0 and 1. So we believe that that provides a much more stable training ground for the student, and so and which ends up performing better. So in conclusion, representation distillation is clearly quite a valuable form of knowledge that can improve student performance, obviously with the benefit of being quite easy to distill, given that we don't actually have to have equal feature dimensions like we do for feature-based distillation. And also with the application of this novel CKA loss, we shift the focus from the scale to the shape and the distribution of the inter-example similarity matrices, which actually dictates the class separation and therefore improves the accuracy as well. And cosine similarity, like I just said, it improves the stability of the bounded of the loss, being a bounded loss, and so that's why we yield better results. And in the future, we sort of expect to apply these to other problems like object detection and image segmentation as well, and we hope to achieve some positive results out of that as well. So in the meantime, that's all from me. So thank you all for listening. I look forward to meeting all of you at the conference. And if anyone has any questions, please feel free to shoot an email my way. I look forward to seeing you then.